You're late, you're late, you're late, you're late. Hurry up, hurry up, hurry up, hurry up. All right, let's roll. So I don't have a lot of announcements except to say that you're in the middle of MP4, and the other announcement is that we don't have an exam this week. I feel like I should make that announcement every week because, I mean, I should talk about exams every week because it's easy to get off the clock, right? So next week we do, and next week's exam will be, we're thinking of it as the MP4 exam, but it will also especially cover lab trees. That lab is really important to the future work in our class, and so we want you to pay close attention to it. All right, that's all I have for the other administrative thing is we are well aware of the drop date, and we're very, very close to being able to give you a sort of a relative standing overview of how you're doing in the course up till this point. So we just haven't quite looked at the numbers enough, but all the data is in the grade book. So we'll be talking about that and let you know within the next day or so. Okay, yes, Neil. No, so so I don't think we've totaled up any extra credit. The data's in the grade book, right? So you can look and see both how you did relative to everybody else on each one of the things, as well as, I don't know if you can, if we have a histogram over all the scores, but I'll be certainly looking at that so I can give you feedback, probably on Piazza. And the way I'm going to do it is, hey, if you scored above, if your average is above blah, you're good. If your average is below something, you might want to come talk to me. Everything else in between, I'm just going to, you are where you are. You can aspire to do better. You can, play defense against playing worse, but I'll probably respond explicitly to the top end and the more struggling end of things. Okay? Yes?
Are all the quizzes counted in like the grade that you calculate, or like
all the quizzes up through 6 for sure. Is 7 in there yet? 7's not. Oh, okay. Through 7 for the quizzes and through exam 2. We don't have exam 3 done yet.
So basically like the lowest for the very top, the second in there.
No dropping. No dropping. We won't do any dropping till the very end. You can account for that in yourself. Okay, let's work. Today's an exciting day. We start the day with a little bit of performance art. So what I need first are 8 volunteers to be actors on our stage today. 8. Okay. 1, 2, 3, 4, 5, 6. You guys decide between the 3 of you. Any hands over here? We're going to choose from other places. All right, 7, 8. All 3 of you can. Okay. Yep. Come on down. You're the actors. Oh, no. Wait. I lost the pointer. Did I bring it? Oh, no. Okay. I'm missing the most important stage prompt. Oh, I've got it. Oh, okay. I have it. It's there. Okay. 7. Okay, I need one more volunteer. Yeah, come on. That's fine. Very good. Okay. So, this really is performance art here, and in our presentation, we're going to need participation from the audience as well as from the actors. So don't think you're off the hook just because, you know, we're doing our thing here. Here's what I want each of you to do. I want you to, from memory, remember where the nodes were on that tree. Just kidding. All right. Uh-oh. There we go. All right. So each of you is going to represent one of the vertices in that tree. And what I want you to do is to stand in this space in such a way that your physical configuration mimics that tree. Feel free to use your arms as pointers and negotiate among yourselves which node belongs to whom. So claim them. And do it as fast as you can. Oh, good job. Okay. All right. Raise your hand if you're the root. Oh, no, you dropped part of the tree. Oh, no. Just kidding. Okay. Yeah. All right. All right. Okay. So what we're going to do here is we are going to personify algorithms. And we are going to be, we are going to be responsible for journaling a lot of what happens. So, and that includes both writing down the questions that you have. I'm going to ask you later if you have questions for our performers. But also to sort of make reflections on the outcomes of the algorithms. Now, this class happens in C++. We're using C++ for implementing the algorithms that we do in this class. And our implementations almost always include keeping track of where we are in the structure via a pointer. That's right. I have a pointer, okay? So what we're going to do here is keep track of our status in the algorithm using this pointer, our state in the algorithm. I have completely messed this up because I forgot to talk about what's the whole point. So let me set the stage. Consider this to be the prologue to the play. That is that we are interested in traversing our structure. And when I say traversing, I mean getting our data out of it. Now, we might not actually pull our data out to keep, but we definitely want an opportunity to see all the data that is included in the structure. Each one of these people now represents a piece of data, and what we're going to do is traverse the structure, keeping track of where, when that data is available to us. Now, so let's begin. So as in code where we pass around pointers, you will all be passing around pointers in such a way that you honor the connectivity of the tree. That is, the arrows that you see in the tree will tell you where you can pass this thing next, right? So, of course, I'm the control freak. I'm the calling function here. I'm going to start by noting that the traversal starts at the root. That's the easiest place for it to start. And I'm going to pass you the pointer, okay?
All right.
Now, you have a choice to make, and your choice is whether you're going to pass it left or right, okay? Now, since you're the root, I'm going to let you make that decision. Do you want to pass it left or right first?
Start left.
Okay, now, hold on just a second. Oh, that's fine. You can keep it. What I want you to all note is that that decision was kind of an arbitrary decision, right? He said, oh, I think I'll go left first. But he didn't have to do that. It's only a cultural decision that made that the obvious choice. And as such, it's a bit of an arbitrary choice. So it's only because it's always been done that way that we will typically go to the left first. Okay, so now, furthermore, because this is an algorithm, we're going to always make that same choice. That is, everybody here is going to be controlled by the same principles. So because, what's your name?
Andrew.
Because Andrew chose to go left, then as well, what's your name?
Derek.
Derek is going to choose to go left first, okay? So Derek, go ahead, go for it. You got to go left, yeah? What happened when you did that?
There's nothing to pass.
Oh no, there's absolutely nothing there. So in our scheme, in our play, what's going to happen is you're going to try to pass it, and it's as if it is immediately thrown back to you by the cosmos, okay? And you recognize it in our implementation world as, oh, that's a little bit of null, okay? Now, we'll keep going for a minute. Now, though, it has come back to you. Do you feel like you are done? Like you have traversed, that you know everything in your subtree has been traversed?
Still pass right.
Yeah, you can still pass right. So go ahead and do that. Okay, go ahead, Mark. What are you going to do first? Left. Yeah, you're going to go left. Okay. What is your name? Boo. Okay. And now what are you going to do? Oh, you've got a challenging thing going on here. What are you going to do? Same thing as everybody else. Yeah. Left. Yeah. And? Yeah. And so then what? Yeah, so you go to the left and there's nothing. You go to the right and there's, and so you are done. You have nothing more to do. You're finished. You can take a nap if you like. Except that first you have to pass it back. You have to let people know that you're done. So yes, your only place you can pass it is back to Mark. Good. Now Mark, what do you think? What are you going to do? Okay, good. Okay. Yeah, good. Okay. Okay, good. Derek, no, you don't get to sit down. That's called the leaking memory if you do that. If you want to sit down, you can sit down right there. Thank you. Okay. Sorry, Mark. Yep, good. And
now we go to the right subtree.
Yep, good. Okay.
I checked that.
Okay.
Nothing there.
Okay. All right. Yay. Yay. Okay. Came back. All right. We are not done here. Here's what I want to know from you, and from you. Who did the most work? Oh, I'm not ready for that question yet. Wait a minute. How many times was each of you handed this thing? So how many times did somebody hand this to you?
Once, except at the very end. Does the end count when they pass that?
I handed it. Yes.
Oh.
Yes.
Oh, 3 times.
Yeah, 3 times you had it in your hand, right? Yes. How about you? How many times did you have it in your hand?
Twice.
Well, or yeah, he handed it to you.
Oh.
And then there's this kind of, the cosmos thing. And then Mark handed it back to you.
Yeah.
So you had it 3 times too. That was the hardest one because it's kind of this weird cosmos part of it. Okay. Now, how many times did you have it in your hand? 3 times, and you? Yeah, it's really kind of like 3 because there's the it gets handed to you, it comes back again, and then yeah, it's a little weird. Okay. All right, same for you. All right. So and etc. So each of you had a hold of this 3 times. Now, suppose that I tell you you have to choose one of those 3 times that you're holding this to yell out your value. Okay? I want you each to choose one of those 3 times you're holding this to yell out your value, and hold up your hand telling me when you'd like to do it. Okay, do you want to do it on the first time somebody gives it to you, or the second time somebody gives it to you, or the third time? There's no right answer here. I'm just trying to get a vote. You're voting on, do you want it to be the, okay, okay. All right, I'm taking this as, I'm going to take the average, and it looks like about a 2 to me, okay? So what we're going to do is we're going to do the traversal again, except that this time, the second time this is handed to you, the second time it's handed to you, you're going to yell out the data contained in your node, okay? Got it? And you guys, your responsibility is to write down the order in which they say their data, okay? You're going to write down the order in which they say their data. Gotcha. Are you ready?
Yep.
Okay. There's 1 for you.
Plus, minus,
Yeah. Say it really loud.
minus.
Good. Thank you. Yep. You should write down minus. Yeah. It came back to you. So you got it. And then there's the Cosmos that holds it for, yeah, now you've got it your second time. So you say, yeah, really loud. Yeah, good. Yeah? Oh, write them down in a line. So minus, and then put your B right there. Yep. Okay? No, she's going to hand it back to you. She's done. And now you have it your second time. So? Yep. Good. You hand it, yeah, and now you say it. Yeah, good. And you hand it back. Good. Back. And?
Plus.
Good. Write down plus. Oh, yeah, there you go. Good. And? D asterisk. D asterisk E. Okay, good. And? Are we done? Did everybody read out there? So how could we check? Do we have 8 things? Do we have 8 people? It's good, right? Wait. D asterisk E. Oh, cool. All right, good. Okay. So now we have a traversal. We have a special name for that particular traversal. It's an algorithmic solution to the traversal problem because every element here made the same decisions as they went. But what I want to know is who did the most work? Who worked the hardest here? Among all of you, whose name belongs in the marquee? Yeah? You did? You had to wait the longest, but who worked the hardest? You think you did? Okay, anybody want to challenge him? You think you did?
I think I worked equally as hard as he did, so he gets the most credit.
Okay, fine. Who else worked as hard as him? All of you, raise your hands. You guys worked as hard as him too? They're challenging your superiority here. Who worked the hardest? Everyone, that's right. Okay, so everyone worked the same amount. Everyone was handed the value, right? Handed the pointer. They passed to the right and got it back. They yelled out their value. They passed to the left and got it back, and they handed it back. Everybody did that. So they all did the same amount, okay? Now, if I had, say, an arbitrary amount of data in this tree, say n vertices, what does that mean for the time it takes to do the traversal if they all did the same amount of work? Yeah, big O of n, that's right. That however much work they did, that's the constant factor times the amount of data that you have. All right. Let me see if I got anything out of this. Okay, if I forgot anything. Okay, do you guys have any questions for our performers? Do you have anything you'd like to ask them? Nothing? You don't want to ask them how much they got paid or like, yeah, do you have a question? What's your reward? Yeah, there's like the cosmos plays a role here. Yeah. I don't know. You can tell me what you would like your reward to be and we can, Yeah, don't even say a word that starts with quiz or exam. Yeah?
Did you guys prepare for this beforehand?
Yeah, did you prepare for this beforehand?
Yes, we did.
No.
A piazza post, very good. Okay, where's my pointer? You need to hand it back. Aren't you guys curious what this is? Like what the heck, right? It's a cell phone holder. You put your cell phone in there, and in fact, it has an LED so that when your cell phone vibrates, it lights up, except I've never actually seen it work. But you can imagine me in the gift shop. This is sitting there right next to the thank you notes or whatever. Like, a pointer, yay! All right. Thank you all very much. All right. Okay, so this is something special. Before I tell you exactly what it is, I want to reemphasize that it is one of many possible traversals. We didn't have to do the traversal in this order. In fact, each of our participants was handed that thing 3 times. They could have yelled out their value at any one of those 3 times. Those correspond to 3 different mechanisms for traversal that we're going to talk about today. All right, so this was play. This is code, okay? Here's the parallel. If I could draw a little pink hand, oh no. We're not entirely, oh, look at that. If I could draw a little pink hand, no, it's on the right slide. That's fine. I'm going to fix it. We're fixing it. Doo-doo-doo. Okay. All right. If I could draw a little pink hand, it would be this parameter. It would be the root parameter here. And we would do the following. So there would be, so the root was not equal to null when we started, right? There would be first this decision to go ahead and pass to the left. Okay, so we would do the same algorithm recursively on the left subtree. And then, as soon as program control came back from that function call, then we would yell out croots data. And then we would traverse the right subtree, okay? These lines here are not meaningful. Now, the special name for this choice of traversal is called an in-order traversal, okay? And it's in order for a reason that we don't know yet. That's a cliffhanger, okay? You'll learn about the significance of the name in order when we talk about our next structure, so later on in the week. All right, but for now, you can think of it as it's called in order because the yelling happens inside the 2 recursive calls. Perfectly reasonable. Okay, any question about the code you see here? I have a question for you about it. Where's the base case in this code? Yeah? Yeah, the base case is when the tree is null, when it's an empty tree. And where is it? Oh no, we forgot the base case. Did we? No, the base case is to do nothing, right? And so that's what happens, it looks like to me. Any question about that? So the base case is implied when C root equals null. All right, any question about it? We do nothing. Okay, well, this next slide is the slide we're going to use to discuss the code that is deployed when we yell the very first moment we possibly can. So the moment I hand the pointer to the node, they yell out their value, and then they make the recursive calls in sequence. This is called a pre-order traversal. So we've got, it's exactly, I used exactly the same slide as the previous one, except that I'm filling in those blanks differently, right? And I changed the question at the bottom. Any questions about the code you see? Is that all right? So we're going to call this on pre-order on the root, essentially. Okay, fine. What's the running time of this function? Yeah, big O of n, that's right. True for in-order traversal as well. Suppose somebody came to you and said, I've got a new tree traversal algorithm. It runs in constant time. What would you say? You don't believe me? Right, good cynicism. That's good. It's good to be cynical sometimes. That's right, because we have to get all of our data out, right? So any traversal algorithm that's a serial algorithm has to at least run in time proportional to the amount of data that it's pulling out. So if somebody comes to you and says, well, I've got a log-in traversal algorithm, you say, I don't believe you. Okay? What if somebody came to you and said, I've got an n squared algorithm? Good job, you guys. Way to go. Right. That's sort of silly, right? We only have n data, and all we're trying to do is look at the data. All right. There's one more technical little piece here, though. There's one technical piece to this. What assumption does this make about yell? What assumption does this argument make about yelling? Yeah? Yes. Whatever we do here, whatever this yell function is, whether it's cout, whether it's a wrapper for cout, or whether it increments the value of the data by 5, or if it is a conditional and it only prints things out if they smell good, I don't know. Whatever it is, yell must run in constant time in order for our argument that this whole thing is big O of n to hold. Okay? Any question about all of that? All right, so here's what I think. I think you, any one of you, can fill in my last slide, except for the last line, without me. So go. Look at the next slide and fill it in. Yeah? So remember that everyone up here, this is a good question. Remember that everyone up here yelled, right? So n pieces of data would incur n amount of work. So you would have n things doing n amount of work. That to me sounds like n squared, right? Okay. A good question. Okay, are you done filling in that next slide? There's a P word that you might not know, but I'll bet you guessed it. Post. Yep, you want me to say post. All right, so here's what I think you filled in on the next slide. You said post order traversal. You called the same algorithm on the left and on the right. And then at the very last possible opportunity, you yelled the data. Okay? All right, any question about it? Is it all right? Of course, I have a question for you. So, this question's a little weird because we have not really talked about an abstract data type, so we don't know what the interface is that we're trying to provide. On the other hand, there are lots of different ways of implementing trees. So I've got a binary tree class. All of these traversals are member functions in them. We need to be able to get our data out in particular orders. What I want to know from you is this function public or private inside the binary, this fictitious binary tree class? Why private? Right. So look, he said it's easier for, it's actually even safer for, and I'll explain that in a second, the client code, if they have a tree, to not have to specify the representation of the root when making this call. This function demands that you've got some idea of how the root is represented. So what we're expecting to do is have a binary tree class B. Okay, a B is a binary tree. And we're expecting to be able to do B dot post order. And all of our data would come spitting out at us. Okay? Now, in order for this to work, it will call our private member function that knows about the way our tree is implemented. So post order, the function, will probably look like this. I mean, the public function will look like this. And you could race me to write this. It simply calls the private version on the root. Okay? Any question about that? And the reason for that is simply that, you know what? I implemented my binary tree with pointers all over the place, but we could have implemented it in an array as well. Who knew? Maybe we could implement it in stacks. I don't know what that looks like, but maybe we could. And the point is that the client code shouldn't need to know that. All right, any questions? Okay, so that's it. That's it. These are our 3 methods of traversing a binary tree that honor the connectivity of the tree. That is where the next thing we could do is prescribed by the left child and the right child. It's suggested a lot by the definition of a binary tree, by the recursive definition of a binary tree. All right, so why did we do this? And the answer is because everybody needs to know about traversals because we want our data out, but there are other applications as well. One of which is simply to make a copy of the tree. Now, this is a review moment. Where have we seen a copy function before? Yeah? Assignment operator, that's right. Where else? Copy constructor, that's right. So if we had this pointer-based, this heap memory-based implementation of a binary tree, we would pretty much be guaranteeing that we would need a copy constructor and an assignment operator, and both of them need to be able to make copies in memory. So let's trace a little bit about what this looks like. So first of all, we're imagining that this is a tree held onto by the root. And in the end, what we're going to want is to return a pointer to, so this one is the new one. The new one points to a copy of the one on the left, okay? Now, here's how it's going to go. We're going to create the root node. So we're going to create the root node. Then we're going to attach something on the left and attach something on the right. What is it that we're going to attach? What is it that we're going to attach? The copy of the one on the left, right? We're going to attach, if this is TL, we're going to attach a copy of TL. If this is TR, we're going to attach a copy of TR. Okay, so let's let that drive our code. We're returning a tree node pointer, that's the thing that we're handing back to the user to use however they like. And so I'm going to get ready, I'm going to build that thing that we're going to return. It looks to me like it needs to be a tree node pointer. I'm going to call it T, and I'm going to ask you, what's a copy of an empty tree? Null. Right, I'm going to set this equal to null, okay? Just for convenience sake, because I already refactored this code a little bit. Now, though, if my thing passed in is not equal to null, then I'm going to do the following. T equal new tree node with value croots data. T's left should become the copy, good, the copy of croots left. And I can do the right since you kind of showed me how. Copy of croots right. And then I'm just going to return T. Okay. Any question about that? I have a question for you. What's the running time of this algorithm? What? What's the running time of this algorithm? Yeah? It does depend on the size of it. How? Oh, the size of the data. I'm not copying any data here, I'm pretty sure. Pretty sure I'm not. Oh, I guess it's creating a new one. Assume it's constant. Assume creating the data is constant. Sure. Yeah, so what's the running time here? Big O of n, that's right. Look what this is. This is like a flower put around traversal, right? Because all that's happening here is a recursive call to croot left, followed by a recursive call to croot right, and then a constant amount of other stuff, right? So we say, pretty cavalierly, we say, oh, the running time is big O of n, it's just traversal. Okay, or we say by analogy to traversal. So this is big O of n by analogy to traversal. Okay, any question about that? Okay, easy peasy. Here's another one. Of course, in the same breath with which we talk about copy, we want to talk about clear, at least I do. Here's the intention for clear. This is the root. In the end, in the end, we want to clear out the data in such a way that the root is equal to null, okay? I have given you a very buggy, almost really pseudo-codey approach to solving this problem, and I want you really quickly to debug it, okay? Fix up this code. Fix this code to clear out the data. Okay, what's the first obvious thing I'm missing? Semicolons and the letter C all over the place, right? Okay, all right, I'll fix that. So this, is that it? C root, okay, good. All right, there's another pretty obvious one. What is it? Yeah, null, this is one I let the compiler tell me this one all the time. Null should be capitalized. Oh, there's one more. One more. Ha, ha, ha. Oh, C root. No, there's two more. Sorry. Same bug. Come on. One more bug. We're all going to ooh and ah at the person who gets it. Yeah? Ooh, now I set you up. Oh. What? Say it again. It's close. It's super close. So it's deleted, but it's not. Anybody else? It's never set to null. That's right. Oh, don't shoot. Okay, so what's going on here? Notice that this function passes the root by value, which means that a copy is made of that pointer. I'm going to do this in red, okay? A copy is made of the root in this thing called C root. Okay? Then the data says if C root is not equal to null, then clear out the left, clear out the right, and set C root, delete C root, and set C root equal to null. Oh. Oops. So how do we fix it? Pass by reference. That's right. We can pass by. There are a couple ways of fixing it. We are going to fix it by passing by reference. Okay? Because then it's as if C root simply becomes another name for the root. And when C root is set equal to null, the root is set equal to null. Okay? Any question about that at all? Is it okay? It's a gotcha for sure. All right, I want to know running time. Big O of n is correct. And of the three other traversals, which one does this most feel like or look like? Yeah, it looks like post-order traversal, right? We've got some stuff going on, two recursive calls, and then some more stuff, right? Or we've got the framework, the two recursive calls, and then our constant amount of work. All right, so this is also big O of n by analogy. And it's like post-order. Traversal. All right, any questions about that? All right. This is like the only time this semester where I actually almost don't have enough material. Like, what? Something's wrong. Okay, so all of the traversals that we've talked about so far, all of the ones that we've given names to, have navigated the connectivity of the tree in memory. Now, there's one traversal that we talked about before, which actually really comes naturally, right? It's called the level order traversal. And it goes something like this. Report all of the values in level 0 of the tree, followed by all the values in level 1 of the tree from left to right, followed by all the values in level 2 of the tree. Now, what does that look like here? It means that we first do that plus. Okay, so the traversal gives us plus. And then it says look at everything at level 0 or level 1, which is all the nodes that are distance 1 from the root, and tell them, report them in left to right order. So it's minus asterisk, and then do the same thing at the next level. That is, in this case, give me all the vertices that are distance 2 from the root in left to right order. Slash D, E. Finally, give me all the vertices that are distance 3 from the root in left to right order. B followed by C. Okay? Now, the problem is that we jump around all over in memory, right? We don't have a way of getting from this node to this node via any references that we've already kept track of. So we need an external ordering structure to do that. That external ordering structure is going to be, raise your hand if you think I'm going to say stack. Raise your hand if you think I'm going to say queue. Again, raise your hand if you think I'm going to say stack. Raise your hand if you think I'm going to say queue. Okay, this is like convergence, right? This is Calc 3. That's going to, Calc 1? I don't know. Where do you get? All right, so yes, it's a queue. This thing right here, we're going to use a queue to orchestrate the visiting or the recognition of each one of the nodes. Now, we don't have time to go through the whole algorithm. You're going to do it on Wednesday in great detail. It will inform what you do for MP4, so it's kind of useful. But I do have a question for you. Before you even see the algorithm, I'm going to ask you about the running time. What's the running time of the algorithm? Is it constant time? No, because that would be nuts, right? Is it n log n? It would be a bummer if all we wanted to do was get our data out and we had to pay a tax to do that. I mean, taxes are great for some things, but for getting your data out, maybe not so much, okay? So if we don't want to pay extra to get our data out, if all we want is our data, how much should we expect to pay? Big O of n, that's right. So the algorithm that we're going to create would disappoint us if it didn't give us linear running time. All right, that's all I got.